Now for Chapter 15 for equilibrium. We're going to be looking at titrations and buffers, still usually referring to acids and bases. For a titration, we're going to be using a burette. You always have a standard solution, so something you know the molarity of, and a sample solution. For our titration, we use our standard. We'll know its concentration already, and we'll use however much volume we use to find the moles. At our stoichiometric point, which we're going to be discussing in a second, moles are equal, and therefore, once I know the moles that I've added to this, and I know that moles are equal, then I know how many moles were originally in here. I can use the volume that we started with to find its molarity. So all that titrations is a way to use molarity to find molarity. So the moles of a standard can be calculated by knowing the concentration of the standard and by measuring the volume used in the titration. Then our equation, mole equals molarity times liters, just rearranging the molarity equation, can be used. The coefficient ratio and the balanced equation can be used to calculate the moles of a sample in the flask here. Knowing the volume of the sample and using the moles from the last step, one can calculate the concentration of our final molarity. So our stoichiometric point, also known as the equivalence point, is the point when the actual mole ratio of our sample to standard is the same as the coefficient ratio. So in this equation here, I have a 1-to-1 ratio. So when my indicator tells me I've reached my equivalence point, that's when this is entirely true. Notice the one-directional arrow. At my stoichiometric point, all of this has been used up, and I have a 1-to-1 ratio of products. Half of what I have is H2O, half of what I have is NaCl. At any other point, I'll have a limiting reactant, I'll have an excess reactant, and the solution will be made up of more than just its products. And the ratio will still be normal, but with excess of one substance. In this equation, notice I have a 2-to-1 ratio of products. So at the stoichiometric point, all of my reactant is used up, and 2-to-1 is the ratio of water to barium chloride in the solution. And this is 100% true. No excess, no limiting reactant. So this is our most common use of titration, is just to find this equivalence point, to be able to use our equation not just for ratios, but for an actual understanding of what is currently in that solution. For example, if I have a solution of HCl and I don't know its concentration, so I use barium hydroxide as my standard to titrate. I know its molarity. My equivalence point is reached, so my indicator tells me I've reached my equivalence point once I've added 14.83 milliliters of barium hydroxide. And I originally had 50 milliliters of hydrochloric acid. Find the concentration of hydrochloric acid in my sample. Well, the standard solution is the one of my known concentration, so that makes my barium hydroxide. First, let's find the moles of barium hydroxide we added. We knew it was 0.15 molar, and at my equivalence point I had added 14.83 milliliters. So I find that I have added 0.022245 moles of barium hydroxide at the equivalence point. Which, since I'm at my equivalence point, that means I can look at my balanced equation and say, well, for every 1 mole of barium hydroxide, I have 2 moles of hydrochloric acid. So if I have 0.022245 barium hydroxide, well, for every 1 to 2, that means I have 0.004449 moles of hydrochloric acid at the equivalence point, because I had a 1 to 2 ratio. So I just use my moles, use the volume I originally had of the hydrochloric acid, so the 50 milliliters, to find the molarity of the hydrochloric acid. I make sure to round to my 3 significant digits, and always be careful that you're putting liters in when you're calculating for molarity, not milliliters. So what exactly is an indicator? Well, an indicator is an equilibrium mixture of a weak acid and its conjugate base. What's important about it is it has different colors when it's in the weak acid form and in its conjugate base form. That way it indicates to us, when we see a color change, that we have converted from a majority of weak acid to a majority of its conjugate base. The color right in the middle of these two different colors will tell us we're exactly in the middle, we're halfway to converting the weak acid to the conjugate base. So to indicate the acidic form of the indicator, we put the IND and we put the H in front of it, because our acid would have the H that it can donate. Its conjugate base form would be minus the H, and therefore have a negative charge because it's lost its hydrogen. These symbols will work for any indicator. For example, if I have an indicator that is yellow in its acidic form and red in its conjugate base form, and I write out my equation. I have the acidic side on this side, its conjugate base form on this side. If reactants are favored, my equilibrium shifts to the left. Therefore, my concentration of my acidic indicator is greater than the concentration of the conjugate base, and it's therefore yellow. You can also just look. If reactants are favored, I would have more of the yellow, and therefore the solution would look yellow to me. If products are favored, then we're leaning towards this side, and therefore the concentration of the conjugate base form is greater than the acid form, and it looks red to me. If there are equal amounts of each, exactly equal in concentration, then we have equal concentrations and an equal mixture of yellow and red is visible to us. Therefore, the color we see is orange. When we worked with phenolphthalein, I had you looking for a very light pink because the two colors of phenolphthalein are clear and dark pink. So the light pink means you're right in the middle of the clear and the dark pink of the acidic and the conjugate base form. That's how we know we've reached our equivalence point for the indicator. Make sure you read this material a few times or rewatch this video to make sure you understand how these indicators work before you move on. This understanding is very, very important to understand why we even use the indicators and what they're telling us. So finding colors of acids and base forms of indicators experimentally. Looking at the equilibrium equation represented by the indicator, adding any strong acid to this solution will increase the hydronium concentration. Why? Well, because any strong acid, HA, will always dissociate into an H plus and an A minus. Therefore, if I add a strong acid, if I add any acid, I'm going to be adding hydrogens, which increases this concentration. So we add away. We're increasing this concentration, which causes equilibrium to shift to the left. Therefore, the solution will turn the color of the acidic side of the indicator. Go over these points a few times to make sure you understand them. So when HCl is added, we shift to the left. My concentration of the left of my reactants is greater than my products. The color will be the same as the reactants. So in summary, and this should be logical, if you add a strong acid to an indicator, it will turn the color of the acidic form. If you add a strong base, it will turn the color of the base form. If you add weaks, it's going to depend on how much you add for the overall effect. So the transition point. The transition point for an indicator is reached when my concentrations are equal. When I have equal concentrations, we see both colors at the same time, so what we really see is this middle color between the two. So the acid form of methyl violet is yellow. The base form is blue. They're always written in the acid versus the base forms. What color would we see at the transition point? Well, we'd see the color in between yellow and blue. So at the transition point, we would actually see green. Find the next two indicators on my list and tell me what colors you would see here. So at this transition point, what effect does this have on its Ka? So if I have my equilibrium equation for indicator, this applies to any indicator, the acid form can be thought of as a weak acid, and we know that weak acids use Ka. So we use our Ka expression, products over reactants. We ignore the water because it's a liquid. The transition point for an indicator is when the concentration of the acidic form and the conjugate base form are equal. And since they're equal, we can cancel them out. So at the transition point, Ka is just equal to the hydronium concentration. Now I'd like to throw in another definition. It's going to be pKa. Well, we know that P, that little lowercase p, always means negative log. pH is negative log of the hydrogen concentration. pOH is negative log of the hydroxide concentration. So if pKa would be negative log of the Ka. So if we take the negative log of both sides of my Ka equals my hydronium concentration, then we get pKa equals pH. Negative log of hydronium is the definition of pH. Negative log of Ka, well, negative log of anything is a lowercase p. So pKa equals pH. Remember, this is only true at the transition point because only at the transition point do we get to cancel out the concentration of both sides of my indicator. How do we know we're at this transition point? Don't forget, that's when my two colors are equal, when we're at the very middle color between the two sides of the indicator. So for now, we can summarize the 4 things we know to be true at the transition point. At the transition point, the concentration of the acidic and the conjugate base form of the indicator are equal. That's why we see an equal color. My Ka of the indicator equals the hydronium concentration at the transition point. pKa, therefore, equals pH. You just take a negative log of both of these, and this is your result. And your color is a 50-50 mixture of the acid and base colors at the transition point. You will need to remember all of this to understand the next material. So titrations are used for what we call volumetric analysis. We use volume to analyze something. That's why with the titration we use our burette, because that burette is so very accurate. It is one of the most accurate pieces of glassware we have, with each little marking giving us exact decimal places. So we use titrations for 2 main reasons. 1, to determine the concentration of an unknown acid or base, or 2, to determine the molar mass of an unknown acid. If I know the molar mass, I can actually determine what type of acid it is, if that is the given question. Every titration must neutralize the original sample completely with a standard solution. A standard solution is the one where we know the concentration and the volume. An indicator must be present to signal the completion of the reaction. Remember, an indicator is our pH-sensitive dyes. If we don't have an indicator, we'll have no idea when to stop adding our volume of our standard. When the original sample has been neutralized completely, the hydrogen and the hydroxide concentrations are equal. This is called the equivalence point. At this point, our volume required for the neutralization to occur is slightly different from the point at which the pH-sensitive indicator changes. We call the indicator change color the transition point, where we call the stoichiometric point the equivalence point. These two have a very tiny difference between them, but it can be significant in some ways. So here are a couple of questions. 1. Why are the volume requirements for the stoichiometric point different from the endpoint? Well, the problem lies in the fact that acid-base indicators themselves are weak acids. So this trace amount of acid that is the indicator has to be neutralized itself. The indicator will only change color after itself is neutralized. The volume difference is very, very small, so indicators are approximating the stoichiometric point. This is also why, whenever you used your phenolphthalein, I leaned more towards a very light pink than the complete middle pink. I would rather have something closer to clear than to the dark pink. How does one prepare a standard solution? Well, there are 2 methods available. 1, direct preparation. We measure the mass of the pure dry substance, and we add a known amount of water. Unfortunately, this only works for certain compounds, like an acid, because our bases tend to be hygroscopic, meaning they hold water molecules which have a large effect on their mass. Our second method is our indirect preparation. This is what we did whenever we were using our sodium hydroxide solution. Because it's a base and it's very hygroscopic, we can't go off of the mass directly from the sodium hydroxide. We need to be able to titrate a base of unknown concentration with a standard acid solution. Then we can calculate the concentration of the base solution, so we use the titration in the reverse direction. That way we now have a standard base. So now for some conceptual questions on strong versus weak acids and bases. First thing I want you to do is go through and answer these questions on your own first, to see if you understand these concepts. Pause the video and do that now. Seriously, just try. Pause the video. Okay, now that you've paused it, you tried them all, I'm looking at you. Now I'll go through the answers. If I was to perform an electrical conductivity test on any acid or base, what would happen? Well, it'll conduct electricity. Why? Well, because both substances dissociate to form ions. That's the basis of any acid or base. It either gives up a proton or it takes a proton. And in the process, it either creates a hydronium ion or it creates a hydroxide ion. So what would happen if we had two acids? They were both strong, but they differed in concentration only. The higher concentration conducts better because it produces more ions. The more ions, the more ability to conduct electricity. What would happen if one acid was strong and the other was weak, but they're equal molar? So they have the same number of molecules per liter. The strong acid conducts better because it dissociates completely, therefore producing more ions than the weak acid. I hope you understood those questions, and I hope you were able to answer those on your own. Next, for competing acids and titrations. When do I write a single arrow or a double arrow for the acid-base chapter? If the question is a weak substance, and it is not a titration, then we'll use the equilibrium symbol to show that the substances compete for the hydrogen ions. So we have a backward and forward reaction occurring. Now notice how I said if it's a weak and it's not a titration. And what this means is that my titrations and my strongs are both going to use the one directional arrow, and any weak acid or weak base will use our equilibrium arrows. So if the question is a titration, neutralization, you will use a single arrow to show that the reaction goes to completion. Like this. Even though we're using hydrofluoric in this reaction, because it is being indicated as a titration reaction, we're going to use our one directional arrow. If you titrate a weak acid and a strong acid that are equal molar, how does the volume of a base required for complete neutralization differ between these two? So how does it differ how much base you need to neutralize a strong versus a weak? Well, for my first example, if I have 25 milliliters of 1 molar hydrofluoric acid, and I use 1 molar NaOH to titrate with it, versus having 25 milliliters of 1 molar hydrochloric acid with 1 molar of NaOH, the volumes are exactly the same. Now, why is that? That sounds weird. It sounds like you would need more base to neutralize a strong. Well, let's look at this problem here, this equation. Now we have HF and KOH, which would be the same thing as HF and NaOH, as the K does nothing anyways. If I continually add this base over and over again, as I'm titrating, I'm adding more and more and more. Well, we know add away. So as I add this base, I constantly am shifting towards products, shifting towards product, shifting towards product. This is why with the titration, we're going to use a one-directional arrow, because we do force this reaction to go to completion. We force it to use up all of the acid. Therefore, just because this is a weak acid doesn't mean it can't be forced to fully dissociate if all these hydrogens are used up to neutralize the hydroxides produced from the strong base. So for part 3, I want you to actually write titration equations. Write the formula, the ionic, and the net ionic equations for the complete neutralizations of the following. I'll do these top two with you. So we start with our molecular equation. Hydrochloric acid plus sodium hydroxide makes sodium chloride and water. Next is to write the ionic equation. So we separate everything into its ions. H plus, Cl minus, Na, and OH. On our product side, water does not dissociate because it's a pure substance, pure water, but NaCl does dissociate. Then we make our net ionic. So we get rid of anything that appears on both sides. Sodium obviously disappears. Chlorine also disappears. So the net ionic equation comes out to H plus OH makes pure water, H2O. So next, if I have hydrochloric acid acting with ammonia, so this time I have a strong acid with a weak base, they react to form NH4Cl. Notice it donates the hydrogen to the base. Therefore, this one acts like a base because it accepts the hydrogen. This one acts like an acid because it donates. However, NH4 is positive, so the chlorine ion will go ahead and attach to it. If we separate anything into its ions, then we have our H plus or Cl minus. And ammonia doesn't separate into ions because it is covalently bonded. NH4Cl does in fact separate into its ions. We do our net ionic, get rid of any ions that appear on both sides, which is the chlorine. So we get H plus NH3 makes NH4. Go ahead and complete the rest on this page. So now we have titration curves. All that a titration curve is, it is graphing the change that we see in volume over the course of a titration. So first, let's look at a titration curve for a strong acid and a strong base. So if I have NaOH and HCl, we know it's a neutralization reaction. We make water and salt. If we look at the product side of the reaction, we make sure that none of our salts undergo hydrolysis, which would affect the ending pH. Looking at these products, sodium chloride is the salt, Na comes from a strong, Cl comes from a strong, therefore this has no overall effect of reacting with water to produce any hydroniums or hydroxides. So all we have in solution is a neutral salt and water. So at the end of this reaction, our pH should be 7. So let's examine the titration curve for the results above when strong substances react together. Well, we started out with HCl in our beaker. So imagine we have our beaker of HCl and we are titrating our base into it. So when we started out with our strong acid, its pH started out at about 1, which makes sense. It's hydrochloric acid. It should have a very low pH. We slowly added milliliters of NaOH. And as we slowly add milliliters, we see a very slow increase in pH. We climb gradually until the volume of NaOH is very close to the volume required for our equivalence point. At the point when we're reaching this equivalence point, now adding a little bit more OH ends up using up the last bit of free-floating hydroniums, and our pH jumps. So now I have more NaOH than HCl. Up until this point, we have more hydronium, hydronium, hydronium. We're adding NaOH, which is slowly using up some of those hydroniums to create pure water. The H and the OH are combining. Then about here, I've now added enough OHs that I use up the last bit of hydronium. So if we're at this middle point, we have the exact equal number of hydroxides and hydrogen ions. This would be our equivalence point. Our final pH is 7 because our NaCl had no effect on the pH. After this point, adding any NaOH is excess. Therefore, my pH goes up and up and up until adding more NaOH has no overall effect. And we reach a final pH of about 13, which makes sense for a strong base like NaOH. So what is the difference here for if we used a strong substance with a weak one? So if my example is HCN, a weak acid, with the NaOH, the strong base. The first question is you must look at the salt and see if it undergoes hydrolysis. Na is from a strong base, NaOH. Cn, well, it could have only come from HCN, and HCN is weak. So therefore, this Cn minus must have an overall effect on the pH at the end. So if we look at its hydrolysis reaction, Cn minus plus H2O, well, the minus will take the positive from the water, and therefore it will produce HCN, and it will leave, I'm going to write this on top, OH minuses floating around. So if we're leaving hydroxides floating in solution, then this salt will increase the overall pH of the reaction towards the basic side. So as we produce product, we also end up producing a little bit of base. So in the end, my overall pH, even at my stoichiometric point, when both of these have canceled each other out, the pH should be slightly basic, because all that's left in the solution, at the stoichiometric point, remember, both of those will have been used up, so all that will be in solution is water and NaCN. But the CN part of this salt actually reacts to form some hydroxide. So at the stoichiometric point, my pH should be slightly basic. So let's examine the titration curve for HCN and NaOH. If we notice, HCN is a weak acid, so we're going to start its pH more about 3. As we add the NaOH, my pH slowly increases, until we reach our stoichiometric point. Our stoichiometric point, or our equivalence point, falls right in the middle of the straight up and down area. So we have our straight up and down area. My equivalence point is right smack dab in the middle, and if you notice, this equivalence point falls more at a 9 pH. So we're definitely not neutral, slightly basic, because of the salt that's occurring at this equivalence point. Past this equivalence point, now we're just adding NaOH to the solution. The HCN has already been used up, so we're adding NaOH, and that will of course increase the pH further. So some characteristics to note in a titration curve of a weak substance. First off, our graph is going to pop up at the beginning when the strong base is added. Conversely, that will pop down if the weak base is titrated with a strong acid. So everything should be the exact opposites based off whatever is in the beaker first. Remember your setup for a titration is we have our beaker with some sort of substance in it. Our pH meter is going to actually be in the substance. So this is what tells us our pH. So this goes in the beaker. So whatever our starting pH is, whatever was the solution we were testing, whatever was in the beaker. The ending pH and the changes in pH are what's happening as we add our titrant. So whatever we see on our graph, if we start with an acid, then our graph should start towards the bottom. Eventually have an up point and curve out. If we started with a base, then our graph would start at a higher pH, eventually go down, and curve back out. And both of these, you'd find your equivalence point at that mid part of the straight up and down. It doesn't really matter which one you start with in the burette and which one you start with in the beaker. What matters is that whatever one you know the molarity of goes in the burette. Let's go back to these notes. So there's going to be a zone on the graph that climbs gradually. So this goes up, or conversely, it climbs down gradually. And this zone is where pH is buffered because the weak substance is undergoing a shift. So we are slowly using up whatever substance we started out with. So here we're slowly using up the hydroxides forming water, which is slowly neutralizing the reaction. On this side, we're slowly using up the hydrogen ions, or the hydronium ions, as we slowly become more basic. The equivalence point will not be at a pH of 7 if we're using a weak substance, because our salt will determine the pH, and if we're using a weak substance, its salt will have an effect. The range of pH values where a suitable indicator can be used is small, because the changes in pH are going to be a little bit more gradual than the strict shape that was given to us with a strong. So look at the following. In each one of these you can tell that we started with the base in the beaker, because our pH starts at a higher level. If you had flipped it and started with the acid in the beaker, you would just take the same thing and turn it this direction. Our data would have ended up the same way. It would just start and end in the flipped direction. Our equivalence point would have still occurred at the same pH. So for a strong with a strong, we end up with a neutral salt, and therefore my pH is 7. If I have a weak base, so notice the pH is closer to 7, and I add a strong acid to it, this up and down area is much smaller because we're using up the base, using up the base, using up the base, and then, bam, drop in pH here because we go down to where our strong acid occurs. Our equivalence point falls at this point on our graph when we look at its pH. If we're adding a weak acid to our strong base, pH starts really high because of the strong base, and our weak acid final pH is pretty close to 7 because it's a weak acid, and my equivalence point falls a little bit above 7 due to the strong base. And if you add a weak with a weak, the pH should end up around 7, but the data is very difficult to read because you end up with such a gradual change, the equivalence point is hard to catch. So generally we use a strong with a weak or a strong with a strong. So I want you to try the following by yourself and then come back and watch me go through it. So pause the video now. Approximate the titration curve that results when KOH is added to HF. So we have a strong base, we have a weak acid. If you can't identify strongs and weaks by this point, you're going to be very much struggling when we hit the test. Select a suitable acid-base indicator. So first we write the neutralization reaction. The two react to form water and KF. You should immediately notice that that K does not play a role. It comes from a strong. So we end up really with an F- ion. We can look at the salt to decide what pH range we're going to be at for our equivalence point. Well, F-, how does this react with water? F- plus H2O, this is negative, so it's going to take the positive from the water, so it's going to produce an HF and an OH-. So it's going to be producing hydroxides. So at the equivalence point, all of this is gone. All that's left is neutral water and this floating ion. This floating ion reacts with some of the water to produce some hydroxide. Therefore, at the equivalence point, we will be slightly basic. Now notice it's only slightly basic because this is just an ion that sometimes reacts with water. So approximate the graph. Well, we started out with a weak acid. So its pH should have been in the middle of 0 and 7. So we start here. Notice we have a gradual pop-up because we added a little bit of OH, which immediately used some of it. And we have this buffering, and we're going to talk about more about buffering, but it's this slow, gradual change until eventually almost all of the hydrogens from hydrofluoric acid have been used up, and we pop up to this point. In this space right between here, right in the middle, our pH should fall into a slightly basic range because of the salt. So I put my pH at about 9, slightly basic. You could be somewhere in this general area. And this would be the point when all of my KOH and HF have been used up. All that's left is the water and my salt, which is slightly basic. Past this point, we're adding KOH and adding KOH without any hydrofluoric acid to react with it. So it just makes the pH go up higher and higher. The KOH isn't playing a role, it's just having its pH measured. The final step was to pick an indicator. So if I was to pick an indicator, I would want one that has a range somewhere between 8 and 10. So that way I can see the color change between 8 and 10. If I picked an indicator that has a range from 6 to 8, I may happen to catch it if the pH change happens at 8. But if the pH change doesn't happen until 9, I won't see a color change at the equivalence point, and so the data would be useless. Let's try another titration problem. Approximate the titration curve that results when HBr is added to LiOH. Select a suitable acid-base indicator. So I have HBr plus LiOH. They react to form water and a salt. Well, I look at my salt and go, well, Li is a group 1 cation, meaning it's from a strong base, so it doesn't do anything. Br is from a strong acid, HBr, and it does nothing as well. That means that my equivalence point must fall at 7 because my water has a pH of 7, my neutral salt has a pH of 7, and both of my reactants are fully reacted in the titration. So therefore, at the equivalence point, the only things that are in the reaction are water and lithium bromide, both of which would have a pH of 7. So I draw it out. This is a strong acid that's being added to a strong base. So I have this nice long middle part. I start out with a high pH, since my beaker contains LiOH, my strong base, to begin with. So I start at a high pH. It gets buffered or slowly decreases until the point at which we're hitting close to this equivalence point, till the addition of HBr has used up almost all of the LiOH. So I hit this point, and now in this transition stage is once all the LiOH has been used up. At this point is when it's equal to HBr. They're exactly at a 1-to-1 ratio. And then the addition of more HBr pushes this down to our lower pH. So at our equivalence point, you draw so that your pH is 7, because what is left in the beaker at this moment is only water and our neutral salt. We would choose an indicator that can indicate a pH change around 7, as that is where our equivalence point falls. For our last example, we're going to look at a titration between potassium cyanide with HCl, and we're going to select a suitable indicator. So I write out my reaction, then I try and estimate its titration curve. Well, in order to do that, I need to figure out where that equivalence point should fall. Looking at my products, I don't have water this time, I have HCN, and I have KCl. So KCl is my salt, so let's see if that will affect the pH. K is from a strong base, Cl is from a strong acid, so neither one of these will affect my pH. The HCN, however, is in fact an acid. So if I have an acid in my solution, even at the equivalence point, then I should have an equivalence point that is a pH less than 7, an acidic pH. So I draw out my titration curve. The problem says that I started with KCN in the beaker and that HCl is titrated into it, so it's titrated with the HCl. So I need to figure out where my starting pH would be. Now you can see from mine that I knew it was a weak base. Notice it's between 7 and 14. Now why did I know it was a weak base? Well, because it's a salt, so you would look at it like a salt, see what it does. Potassium does nothing, it's from a strong. Cyanide, however, when it reacts with water, is going to form OH minus. So if we need to see that, Cn minus plus H2O is going to produce, notice how this is negative, so it's going to take the positive away from the water. So you get HCN plus OH minus. So this original KCN that was in my beaker had these OH minuses floating around in the solution. So I had a pH of a weak base. If it was a strong base, it would be one of the ones we have memorized. So I start out with a pH of a weak base, and I'm adding a strong acid to it. So I know that my end point, so I have a starting point, and I know my end point will be in the strong acid area. Now where do I draw out my equivalence point area? Wherever you're drawing your equivalence point area, that's where your straight up and down area goes. Well, we said that at the equivalence point, we'll be slightly acidic. So at this point, slightly acidic is where we're going to aim to put our equivalence point. We know that our equivalence point falls on a straight part of our titration curve. So once you have a starting point, an end point, an equivalence point, make sure you make a straight line in the area of the equivalence point, because the equivalence point falls in the halfway point of your straight line. Then you just connect the rest of it. So you would connect to your straight line, then connect your straight line on to your final point. Now for some final pointers on hydrolysis. Remember hydrolysis, hydro means water, lyse is to split or break up. This is when our ions will split or break up water in order to form hydrogen or hydroxide ions. If you're forming hydrogen ions, you're creating an acidic solution. If you're forming hydroxide ions, you're creating a basic solution. So we have two different types of oxides. We have metal and nonmetal oxides. Metal oxides are made of a positive ion, such as calcium. This positive ion will react with the water to take the negative ion from water, the OH minus part. It creates a basic compound. Nonmetal oxides, they combine with the water. Therefore, we end up with these nice H's in the front, able to donate protons. So we create acidic solutions. So given the example of Na2O, notice Na is a metal. Therefore, when it reacts with the water, it takes the OH and makes a base. For SO2, sulfur is a nonmetal, so it's a nonmetal oxide. It combines with the water to create H2SO3. We literally just add them all up together. There's two H's, one S, three O's. A couple last pointers for acid rain as well. Remember that acid rain has a pH less than 5.6 because normal rainwater has a pH of about 5.6 to 6. So why does normal rainwater have the pH indicated above? Well, the CO2 in the air combines with H2O to make the water slightly acidic. Notice CO2 is a nonmetal oxide. CO2 plus H2O would make H2CO3. Add it all together. A reminder from your chapter 14 notes, what are the two major sources of acid rain? NOx and SOx. So nitrogen oxides and sulfur oxides. Any number here would fall into those X's. Because whenever our nonmetal oxides react with water, you just add it all together, which would automatically end up creating some sort of acidic solution. Now what do we do with our polyprotic acids? Remember, polyprotic means poly, more than one, protic, meaning more than one proton, and our proton is just the hydrogen ion. So it's an acid that has more than one hydrogen. How would we do the titration curve then? Because it can lose one hydrogen at a time. So we're going to see several changes in pH and a few equivalence points. Well, with these polyprotic and polybasic substances, each proton is transferred to or from the chemical species in a stepwise fashion. Remember, one at a time. So to complete the transfer of each proton, you end up with an endpoint at each point. Therefore, if the acid is diprotic, there should be 2 points on the titration curve that represent these endpoints. So let's assume that the titration curve above, which in this case I moved it to the right, is for the titration of H2SO3. Why is the first endpoint acidic, referring to this one? Well, HSO3, when I've lost this first hydrogen, is an acid. Therefore, the solution after this loss of the first hydrogen is still acidic, and its equivalence point would still be in the acid range, right here. Now this continues to change as it's titrated with a base. Notice the pH is going up. And eventually we hit a second equivalence point where we have lost the second hydrogen. And in this case, the pH is in the basic area because SO3 2- is a weak base. So at this point, the solution has SO3 2- left over and is therefore basic. Which indicators would you use? Well, we'd need two different indicators, two distinct indicators. So we could see a color change here, and then our second color change here. For polyprotic acids, you really only need to be able to read one to understand what it is that you're looking at. Here's an example for H3PO4. read through this to double check that you really understand what's happening with these titration curves. Now for buffers. So first let's think of what the word buffer means. If you think of a buffer between siblings, that's the person who kind of calms everything down, who keeps everything neutral. A buffer does that. It keeps things from changing too much, from becoming too acidic or too basic. It keeps the pH constant. This video here comes from MIT, and it's a very important video that gives you a lot of demonstrations and information on how to visualize what a buffer is. Go ahead and watch the video and take notes on a separate sheet of paper that you're going to staple to the back of your note packet. That will be part of the grade for this packet. Each time he asks you to pause the video, do so and write down your ideas for each part. If your ideas are incorrect or if you can't think of an idea, at least write that down. Write what you know and what you learned after he explains it. So now that you've watched that video, I'm going to go through my notes with buffers, but make sure you keep those visuals in mind as I go on. A buffer solution is a solution in equilibrium that will maintain a relatively constant pH when small amounts of acid or base are added to them. So how do we make a buffer? Well, we need two things. First, a weak acid or a weak base, and second, a weaker conjugate substance in the form of a salt. Meaning we need to have an original concentration of weak acid and weak base, and its conjugate, something that's already on the product side. So let's prepare a buffer solution using acetic acid. Acetic acid is a weak acid, so that's my first requirement. If we write out our equation, we know that acetic acid separates into a hydrogen ion and CH3COO. However, because this is a weak acid, we end up with a high concentration of our weak acid and very low concentrations of the ions that it ionizes into. So we said that the second thing we need for a buffer is the conjugate. We need to have conjugate inside the solution. So we need to identify the conjugate, and our conjugate in this situation is obviously our CH3COO. We need to add a salt that contains this ion in order to increase this concentration. Just for a general note right here, notice these concentrations. Right now it's high, low, low. What we want is a high concentration of our weak acid or weak base and a high concentration of its conjugate. The easiest way to get a high concentration of its conjugate is to find some salt that contains that ion, a soluble salt that contains that ion. In other words, take this ion and put an Na or a K or an NH4, something that's entirely soluble in front. So now my equation looks like this. I have my weak acid. It's going to separate into its ion and it's going to produce some of this. But in order to call it a buffer, I went ahead and added this salt. So that way I already have a high concentration of this CH3COO. Now why? Why did I add the salt to make this a high concentration? What is the use? Well, I have a couple reasons here. First, a weak acid that does not have the salt is not an effective buffer if the acid is added. Because if I add an acid, that's going to increase this concentration, add away. It's going to cause a massive shift in concentrations, and therefore a massive shift in pH. If I start with a weak base, without its salt, the same thing will happen. Adding a base to it would create a change to our concentration of OH, which would be here, and it would once again create a massive shift in our equilibrium, and therefore a shift in our pH. We said a buffer resists change in pH, so we must have a way of doing that. By having this high concentration here, that's how we're going to resist it. So why is the buffer ineffective without the salt? Well, there's only a small concentration of the conjugate species, when the weak base or the weak acid actually separates. Remember, when we called something weak, we're generally saying less than 5% of it actually separates. So what that means is that in equilibrium, I have a very tiny concentration on the right. So how would adding a salt convert our solution into an effective buffer? Why does this high concentration help this? Well, the addition of the appropriate salt will increase the concentration of the conjugate species. This allows the equilibrium to shift a significant amount of material to the left and the right. In other words, it allows Le Chatelier's principle to apply without significantly changing our concentration of hydrogen or hydronium, which are the only two things that would affect the pH. So by having a high concentration here and a high concentration here, we can shift left and right, without really affecting this middle amount. Therefore, my pH doesn't change. So what happened to the ion that didn't play a role, meaning what happened to the Na? Well, it's a spectator ion. It's always a spectator ion. It has no effect on the solution. How do I ensure that the spectator ion will always be a spectator? Only choose cations from group 1 or 2. Only choose things that we know are soluble and don't play a role. In other words, pick ions that come from strongs. Remember when we were talking about hydrolysis, which ions actually affect the water? Well, it's things that come from weak acids and weak bases. So you want to choose ions that definitely come from strong acids or strong bases, so they do not have an effect on the pH themselves. You want them to be independent of affecting the pH. The only reason we add the salt, like in this case, was to increase the concentration of the conjugate ion. So let's do some practice. If we were to prepare a buffer for this solution, I have HCN, and it will always break apart into its ions H and Cn minus. Now it's a weak, so we have a high concentration here and a low concentration of each of these at equilibrium. In order to make this into a buffer, I change this concentration into a high concentration. That's the only thing we're doing when we're creating a buffer. We're taking a normal weak reaction and adding something, specifically a salt that contains our conjugate ion, in order to have a high concentration of the conjugate. Our goal is always to have a high concentration of the weak acid or weak base and a high concentration of its conjugate. So for the reaction of NH3 with water, it produces hydroxide and NH4. The conjugate of NH3 is therefore the NH4. I want a high concentration of both the weak base and its conjugate, so add a salt. That would have NH4. Any salt, just a salt that contains NH4, would therefore increase the concentration of NH4 to be high, and therefore you have a buffer. So given these two buffers, we have a couple questions. First, what will happen to the overall pH of both buffers, both this one and this one, if we added a small amount of acid? Well, in this first case, adding an acid would therefore be adding hydrogen ions. The acid will obviously dissociate to produce some hydrogen ions, and therefore we're increasing the concentration of hydrogen ions. So we add away, and we shift to the left. Adding an acid to this base would be adding hydrogen ions, but hydrogen ions aren't in this equation, so what effect would adding a hydrogen ion have? Well, adding a hydrogen ion will attract these hydroxide ions here, creating water. Creating water will have no effect on the pH, but it will shift our equilibrium because they will be taking away the hydroxide ion concentration. So if we take towards, we shift to the right. And the pH of both of these will decrease slightly. In this first reaction, we increased the concentration of the hydrogen ions. Now we do shift to try and compensate for this, but overall there will at least be a tiny increase in the hydrogen ion concentration. Therefore, a lower pH. The higher the hydrogen concentration, the lower the pH, because it's a negative log of the hydrogen concentration. Now for our second buffer system, since we're taking away the hydroxides, that would actually bring us to be less basic, therefore decreasing the pH. So question, can HCl be used to make a buffer? No. We said that all of our buffers must be made with a weak acid or base. HCl is a strong acid, so it does not even form an equilibrium system. An equilibrium system is able to shift in either direction to buffer or limit the amount of change caused by the addition of an acid or a base. Because strong bases don't even enter equilibrium or don't have these double-sided arrows, it's not possible for them to be able to compensate back and forth to limit the change in pH caused by the addition of an acid or a base. Which of the following salts would be the best choice for preparing a buffer for NaHC2O4? Well, we always said we need our conjugate, which in this case will ignore sodiums because sodiums don't ever play a role. So ignoring our sodiums, we have HC2O4. Its conjugate would be what happens once it loses its hydrogen, and therefore we're looking for C2O4. So NaC2O4 is the conjugate species from what we were given. So this would be a perfect salt to create a conjugate for this acid. And therefore, by having a high concentration of both of these, you would create a buffer solution. Now for some calculations with buffers. Since buffers are equilibrium systems, the calculations that govern them are the same as any other equilibrium problem. We use an icebox. First, you calculate the approximate pH for a buffer prepared using 1 molar acetic acid and 1 molar sodium acetate. Well, first, we'll write the dissociation equation for the weak acid. Second, we'll prepare our icebox. So we write our equation, we set up our ice, ICE, we have an initial concentration of 1 molar for our CH3COOH. We have an initial concentration of 0 for our hydrogen ion concentration. But notice it said we made this buffer using 1 molar sodium acetate. Now I don't include the sodium in my equation, but my acetate ion I do include. And I said it was 1 molar. So you include that in your ice table. From there, it's just normal equilibrium calculations. You'll use your Ka and plug in your equilibrium concentrations. Now notice, we've always been able to call this X insignificant for our original concentration from our weak, because we know it dissociates less than 5%. Now, because we have an initial concentration of our salt as well, we can also call this X insignificant. So you would say overall, the change in concentration is insignificant compared to the original concentrations of our weak acid and its conjugate salt. When you plug these numbers into your Ka, you get the following. X times 1 over 1. Plug in your Ka, you solve for X, and you have your hydrogen concentration. From here you can simply solve for your pH the way you always have. Your hydrogen concentration, take a negative log of that, and now you have your pH for this buffer. And because it's a buffer, we know there won't be any significant change to this pH from the addition of small amounts of acid or base. Now for your next problem, you're going to calculate the approximate pH of the buffer prepared using 2 molar NH3 and 2 molar NH4NO3. We know this is a buffer because it says it, and also we have a weak base and its conjugate salt. We write out the reaction. We know it's a buffer because we have a high concentration of this and a high concentration of this. Set up our ice table, ignore the pure liquid water, put in our initial concentrations. I initially have 0 of the hydroxide. Put your changes and we call our x's insignificant in our concentration change for NH3 and NH4. So we plug in these amounts without the changing x's. We get x times 2 divided by 2 equals Kb. Unfortunately, you're often given Ka instead, so you would convert your Ka of NH4 using Kw, 1 times 10 to the negative 14, into finding your Kb amount. So you plug it all in. Kb equals products over reactants. Plug in our Kb, plug in our equilibrium concentrations, solve for the hydroxide concentration. This asks for pH, so we turn our hydroxide concentration into a pOH and subtract from 14 to get a pH of 9.25. Don't forget that sig figs for pHs fall into the decimal place. The last 3 problems are for you to complete on your own and will be checked when you turn this packet in. I want to see that you at least attempt number 5, but if you get the correct answer for number 5, you can get extra credit for the packet. Now for some quick notes before I get to the very last 2 pages with you. If I was to draw a graph of pH versus time, when I add a small amount of HCl to a buffer, so my pH stays constant, I add HCl. So if I'm measuring pH, my pH should drop with the addition of HCl. And it does. However, because buffers are made with weak acids or weak bases, they are made to shift using Le Chatelier's principle, and it does. It shifts to bring my concentration of my hydrogens back to their original amount, or as close as possible. And by bringing the concentration of hydrogens, we therefore are bringing our pH as close as we can back to its original pH, which means overall we have a net decrease in pH. But it's very small because in using a weak acid or a weak base, we're able to use Le Chatelier's principle to compensate for these additions of acids or bases. So if I was given this buffer system, using sodium acetate as my salt and acetic acid as my weak acid, I look at pH versus time, and I'm adding NaOH, I'm adding a base. So my pH is constant until I add a base, and logically we see a rapid jump in the pH towards the basic side. However, because we make buffers out of weak acids and bases, in this case a weak acetic acid, my shift is able to bring this back down. So let's think this through. We added NaOH. Now NaOH doesn't actually play a role in this equation, but the OH minus does. Because the addition of OH minus will react with the H3O to form waters. So even though we're adding OHs, and that does cause an initial increase in pH, these OHs are used up with the H3O to produce water, which brings the pH back to its original concentration amounts as close as normal using Le Chatelier's principle. A very slight change in hydrogen or hydronium concentrations, and therefore a very slight change in pH. Now a titration problem. The following titration curve results from titrating 25 milliliters of 0.1 molar weak acid. Notice we know its molarity, so therefore this is our standard. It's being titrated with a strong base. If we look at this, we can estimate the Ka. Well, we know that at our equivalence point, my pKa equals pH. And we can tell that at our equivalence point, my pH is about 9, maybe a little bit higher. So we'll say 9.2. So this is our pKa equals about 9.2. So how do you find a Ka? Well, anytime you have a P, you do the opposite of it. So the pKa means it was the negative log of the Ka. To do the reverse of that, you would do 10 to the negative 9.2 equals your Ka. Put your answer here. Now we can also use this graph to calculate the concentration of KOH. We know from our standard that we use 25 milliliters of 0.1 molar weak acid, which in moles would be 0.1 times 0.025. So 0.0025 moles of our weak acid. Now notice for our KOH this has a 1 hydroxide, which means my acid and my base have a 1-to-1 ratio. So now I have 0.0025 moles of KOH as well at my equivalence point. Also, at my equivalence point, I can find out how many milliliters I used. Looks to me I used about 17. So if I have moles, 0.0025 moles, at exactly 0.017 liters, now I have molarity. Solve and write your answer here. We have 2 more questions. First, a buffer solution using 1 molar NH3 and 1 molar ammonium chloride. First, write the equilibrium expression. We start with our weak base, we look at its dissociation, and we have a high concentration of its conjugate. So NH3 plus H2O makes NH4 and OH minus. When a small amount of HCl is added, the OH is going to quickly decrease. Now why? Because if we add HCl, we're adding hydrogen ions. Hydrogen ions like to go off with hydroxide ions to form H2O. Therefore, we're using up some of these hydroxides and lowering the pH. We're getting closer to neutral. We're becoming less concentration of hydroxide and more water in general, so therefore a pH closer to 7. As a result, my equilibrium is going to shift to the right. Why? Because I did take away towards. And the concentration of hydroxide will eventually increase. The pH will go back up. So as a result of adding the HCl, there's a small net decrease in the hydroxides. Because eventually this will be used up and compensated using shifts using Le Chatelier's principle. But overall, there must be a tiny decrease because it did get used up by reacting with the hydrogen ions from the HCl. If I was to draw a graph of this using my concentration of hydroxide versus time, it would be very similar to what I showed you of using pH versus time. We have our hydroxide concentration on our y-axis, time on our x-axis. Our hydroxide concentration is constant until we add HCl. This, of course, uses up some of this hydroxide concentration, but because this is in a buffer and it's in an equilibrium system, it's able to shift to compensate, trying to reproduce some more hydroxide. By shifting to the right, more of this reaction occurs, producing more of this. So we overall only have a small decrease in the concentration of OH, and therefore overall a small decrease in the overall pH change. If you were to draw a graph of pH versus time, it would look the exact same. pH and OH concentration, after all, are directly related, using a negative log of the hydroxide concentration and comparing that using the number 14, because the pH plus the pOH would equal 14 at 25 degrees Celsius. And for the last question, I expect you to be able to fill this one out on your own. If you have any difficulty, make sure you ask questions. I hope you've worked through this whole packet and you've actually spent the time to learn this material, as this will be all part of your test. Equilibrium is a very crucial concept, and acids and bases can be difficult to wrap your head around. So make sure you've actually spent the time to work through this and ask the questions you have.